Okay, let's jump right into this explainer. Today, we're exploring a completely groundbreaking new study that finally lets us see the invisible magnetic fields churning deep inside our sun. For the longest time, the internal dynamics of our closest star have been totally hidden from us. But thanks to some incredibly clever new research by Samideep Chatterjee and Gopal Hazra, we are now quite literally reverse engineering the sun's magnetic engine. But it really begs a fascinating question. How exactly do you look inside a star? I mean, we can't exactly shoot a probe into the crushing million-degree plasma of a stellar core, right? And because of that extreme environment, predicting the sun's internal magnetic engine has been this massive cosmic mystery for decades. Even our most advanced observational techniques couldn't directly measure the magnetic fields buried deep in the solar interior. We've essentially been staring at a locked box, only able to see what pops out on the outside. And what happens on the outside is entirely driven by this hidden engine, which powers the solar cycle. That's the roughly 11-year cycle of the sun's magnetic field. Think of it like this. That internal engine pushes its magnetic exhaust up to the surface in the form of sunspots. And the placement, the frequency, and the sheer intensity of those sunspots absolutely dictate the space weather we experience right here on Earth. So here is our roadmap for how we're going to break this all down. We'll start with the space weather threat. Then look at the solar black box, dive into 3 decades of data, reveal the sun's guts, and finally see how we're predicting the next cycle. Kicking things off with Section 1, the space weather threat, and why predicting the sun's mood is so crucial. The thing to remember here is that understanding this magnetic engine isn't just some abstract academic exercise. It's actually about safeguarding our planet. Look, if we want to protect our orbiting satellites, our global communications, and our terrestrial power grids from massive solar storms, we absolutely have to figure out how our star works on the inside. Those surface manifestations, the sunspots and flares, they're just the symptoms. To predict space weather accurately, we have to understand the underlying disease, so to speak, which is that internal magnetic field generating them in the first place. Moving along to Section 2, the solar black box and the real limitations of traditional observation. So, for a long time, scientists were just hitting a brick wall. We simply couldn't see inside. Not even studying the acoustic waves of the sun could directly measure that buried magnetic field. To get around this massive blind spot, researchers had to completely flip the script. They tossed out the old way, which relied on simplified 2D math and, frankly, a lot of blind guessing about how sunspots might behave. Instead, they pioneered a new way. They are using 3D data assimilation. Basically, they're taking huge amounts of daily, real-world surface observations and working backward to reverse engineer the interior. Instead of trying to guess the physics from the inside out, they're finally using hard data from the outside in. Which brings us to Section 3, 3 decades of data. Specifically, the assimilation of MDI and HMI magnetograms. To pull off this reverse engineering feat, the researchers used 30 years of data from space observatories. They captured the surface every single day between 1996 and 2025. And they built this brilliant 4-step pipeline to handle it all. Step 1, collect the daily surface magnetograms. Step 2, drastically reduce the noise and map everything to a specific grid. Step 3, extrapolate those surface fields deep down into the sun's convection zone. And Step 4, compute a 3D toroidal source term, which just means calculating the magnetic lines running vertically from pole to pole. Basically, they figured out how to translate daily magnetic exhaust into the raw fuel for an internal simulation. When you map out this exact pipeline, you see how raw observational data from the surface gets transformed into an incredibly realistic 3D dynamo model, which they call stable. By running this assimilation daily, they accurately conserve the magnetic flux, meaning their model perfectly matches the real-world sun, day by day, year after year. It's honestly amazing. All right, on to Section 4, revealing the sun's guts. This is where we finally get to visualize the magnetic engine in full 3D. This is where the curtain finally gets pulled back. Notice how surface sunspots aren't just flat little patches painted on the sun. They are actually complex magnetic tubes anchoring deep down into the convection zone. You've got these red and blue areas indicating positive and negative polarities, and you can clearly see how the larger active regions reach even deeper into the solar interior. It's a huge realization. The surface activity is physically and deeply tethered to what's happening on the inside. And by tracking all this data dynamically, the stable model reveals the breathtaking 3D reality of the toroidal field. Those are the magnetic lines wrapping horizontally around the sun's equator.
Check out those bold red and blue bands. Those represent the sun's internal magnetic guts. At the start of a solar cycle, they form up at the higher latitudes, but as the cycle progresses toward its maximum, you can literally watch these powerful bands migrate toward the equator. This equatorward migration is a fundamental mechanism of the solar dynamo, and we are finally seeing it with incredible clarity.
Now, you might be thinking, okay, cool, but how do we know this model is actually accurate? Well, we know it works because they validated it against separate historical data. When they compared their simulated outputs to real-world data from the Wilcox Solar Observatory, it perfectly matched 3 decades of reality. It nailed everything from polar reversals and overall magnetic strength to the weird variations we see from one cycle to the next. So this simulation isn't just generating pretty pictures, it is fundamentally mirroring the true physical reality of our star.
And that brings us to our final section. Section 5, predicting the next cycle and forecasting solar maximums years in advance.
Look, the ultimate payoff of any scientific model is whether or not it can forecast the future. So the researchers put it to the test by deliberately cutting off the observational data feed years early. For example, they stopped feeding the model entirely in the middle of 2011, well before the peak of solar cycle 24. And impressively enough, the simulated internal engine just kept on running on its own physics, and it correctly predicted the peak of cycle 24. It maintained total accuracy without needing those daily surface updates to hold its hand. And the results were highly consistent across multiple tests. By constantly assimilating daily surface observations, we can now confidently predict a dangerous solar maximum up to 3 to 4 years in advance. I mean, just pause and think about that for a second. That is 3 to 4 years of lead time to prepare our power grids, adjust satellite operations, and protect critical infrastructure from massive solar storms. That's a huge deal. This completely changes the game for planetary defense and space exploration, and honestly, it leaves us with a really fascinating thought to close on today. If reverse engineering mere surface data, literally just looking at the daily exhaust, can successfully reveal the deeply hidden 3D magnetic engine of a star, what other massive cosmic mysteries could we unravel simply by studying the surface of things? It just goes to show you, sometimes the answers to the universe's deepest mysteries are hiding right in plain sight, just waiting for us to build the right model to read them.